Hi, my name is Ingo Müller, and today I'm going to present Lambada, a system that we built in order to study serverless cloud infrastructure in the context of data analytics. In this work, we identify a number of challenges with that type of infrastructure and show solutions to overcome them. By building a full-fledged system, we are able to show that serverless infrastructure is mainly attractive for interactive analytics on cold or infrequently used data. Let me start with a quick definition of what we mean by serverless computing. We mainly refer to serverless functions, where the user writes a function typically in a high-level language, installs it to the cloud, and later calls it with some input. It is the responsibility of the cloud provider to schedule and execute that function and return the result to the user. This is interesting for the user because it frees them from a number of management tasks. Furthermore, the pricing model is attractive because it is fine granular and usage based. Finally, this is really attractive because the cloud providers are able to scale the number of locations to a large degree, often to several thousands. People have early on understood how powerful this idea becomes if we make that function f a higher order function that we can call with the lower order function g and get the result of g applied to x back. This is powerful because we can use that high degree of parallelism to run arbitrary computations. And people both practitioners and researchers have been really excited about this. They like the elimination of cluster management overhead, and they see the promise of elasticity, and they like the millisecond level pricing. One formulation that I really like is the following. Somebody said that the cloud thus becomes a burstable supercomputer on demand. At the same time, people have found limitations of this approach. Maybe the most severe one is that different function invocations cannot communicate directly between each other. And what people have done instead is to use existing storage system for indirect communication. In general, there are some resource limitations that make it challenging to use serverless functions, in particular for moving around large amounts of data. The alternative of indirect communication has these problems on their own, in particular request limits of the existing storage systems. And maybe the most negative verdict that we found is one by Hellerstein et al. That was published last year at CIDR, which said that current serverless offerings are a bad fit for cloud innovation and particularly bad for data systems innovation. So between these two extremes, we wanted to know, how do serverless really fare in the context of data analytics? Otherwise put, in which scenarios, if at all, is serverless viable for data analytics? And as a first part of the to answer that question, we ran a simulation of scanning 1 terabyte of data from cloud storage. And we're using different types of platforms for that purpose. If we use one single virtual machine that we start particularly for that job, that takes in the order of 30 minutes and costs a couple of cents. Of course, we can parallelize that scan and use more virtual machines, and what happens then is the following. As we add more virtual machines, the runtime is lowered as we expected. However, at some point, the running time is dominated by the startup time of a virtual machine. Similarly, we need to pay for the startup time of this large number of virtual machines. So as we add virtual machines, that startup time eventually dominates the cost. If we use serverless functions instead, what we get is the following. We have a similar shape, however, at a different place in the space-time trade-off, in the cost-time trade-off. Comparing the cheapest execution, serverless functions are about an order of magnitude more expensive than virtual machines. At the same time, since the startup time of one function is a second or less, we can parallelize to a much higher degree and get an overall much lower running time in the order of less than 10 seconds. What this tells us is that we should use serverless functions only if we're interested in this low latency, in that interactive range. Otherwise, we could use virtual machines and get the same job done at a much lower price. If we're targeting interactive queries, we could also spin up virtual machines and keep them running in order to eliminate the startup overhead. So we extended our simulation to that scenario and used 3 different types of virtual machines that preload the data to 3 different levels of the storage hierarchy. All of the clusters are sized such that they can scan 1 terabyte in 10 seconds. The costs look like the following. Depending on the number of virtual machines in each cluster, there's a certain cost, but that cost is fixed per time. In particular, it is independent of the number of queries that we run. That is in opposition to serverless functions, who have this usage-based pricing model and thus a linear relationship between the number of queries and the cost. At some point, there's a cutoff. In our simulation, that's 16 queries per hour. If we run less queries per hour, then that usage-based pricing model makes the functions more attractive. If we run more queries, then the fixed infrastructure results at an overall lower cost. So putting these 2 insights together, we can now understand that serverless functions are mainly attractive for interactive analytics and on cold or infrequently used data. The remaining of the talk, I will present a system that we built in order to understand whether the reality looks like this and whether our simulation is realistic. The system that we built is called Lambada, and the architecture looks as follows. On the workstation or laptop of the user, there's a component called driver, and all other components are components in the cloud. In particular, here illustrated with lambda symbols, we have workers as serverless functions and different types of storage managed by the cloud. When a query is written in our system in some high-level Python frontend, when a query is executed, it is transformed into a query plan, and that query plan is given as an argument into a large number of serverless workers. Initially, the data is on S3, and each worker downloads a slice from that input into its local memory and applies the plan in a data parallel way. If, as part of the plan, the workers need to communicate, they need to do so through external storage, because, as I briefly mentioned earlier, the cloud providers do not enable direct communication between the workers. At some point, each of the workers has produced its result, posted to some message queue, and on which the driver is polling, such that it can eventually show the result to the user. Now, you've probably understood that this is a classical shared storage architecture from a high-level point of view, except that all of the components are some components in the cloud that are to some degree serverless. What I want to say with this is that all of these components only incur costs while queries are running, and there is strictly 0 cost between queries. This is somewhat in opposition to the system that we will see just in the next presentation, Starling, who still have a coordinator that is running even between queries and usually orchestrating the work during the queries. However, it is incurring costs also between queries. Now, while this is a traditional architecture, we still had a number of challenges to solve, and the challenge starts with the mere invocation of a large number of functions. The problem is that the driver cannot place more than a certain number of requests into the cloud through the internet per second, such that it becomes the bottleneck. And what we did instead is a 2-level invocation where the first number of workers helps invoking the remaining workers. Also, we had to be careful with how to do the in situ processing from cloud storage. In particular, we wanted to download only the required bytes for this particular query, and we achieved that by pushing the selections and projections into the file system abstraction. Finally, and maybe most importantly, we built a shuffle operation that works around this absence of direct communication and goes through cloud storage instead. People have attempted that in the past, but thought that this inherently does not work in the serverless setup due to the request limits of the that the cloud providers have on cloud storage. However, we were able to devise a 2-level shuffling algorithm that and equipped it with some other optimizations that overcomes these request limits. And in the end, we were able to scale to several thousand workers and shuffle several terabytes in less than a minute. Let me show you some evaluation on TPCH queries, scale factor 10,000, and compare them with other serverless solutions, namely the two query as a service systems, Athena and BigQuery. If we look at BigQuery, we first notice that it cannot process the data in situ, but needs to load it first, and that takes quite amount of time, almost 1 hour. If we do not take that into account, or starting from the second query, BigQuery is the fastest system in the comparison with a low single-digit number of seconds. Athena is still interactive with a running time of less than a minute, however quite significantly slower than BigQuery. At the same time, it's also almost an order of magnitude cheaper. If we put Lambada into the picture, our serverless system, that is another order of magnitude cheaper, and depending on the configuration, has a running time of that query of less than 10 seconds and is therefore clearly interactive. Overall, this shows that serverless can have interactive query speed, and in particular at a significantly lower cost than commercial solutions. In conclusion, we can say that the serverless paradigm is interesting for interactive use on cold data, and one might add, mainly for that use case. However, in that use case, it can outperform commercial solutions in both cost and speed significantly. At the same time, there's still some challenges in the serverless paradigm that require custom solutions, and we believe that this has a rather narrow window of economic viability. If our use case is not interactive or not on cold data, then traditional virtual machines are maybe still more attractive. That concludes my talk, and I'd be happy to answer questions.